Hello, and thanks for joining us today for the latest Analytical Cannabis webinar, the Analytical Landscape of Cannabis Testing, Session 4, Residual Solvents and Terpenes by GCMS. I'm Karen Stewart from the Analytical Cannabis editorial team, and I'm here to moderate today's event. I'm really pleased to have Kirk Jensen and Sean Orlowicz joining us today as your presenters. Kirk graduated from the University of Northern Colorado in 2005 with a bachelor's degree in chemistry, after which he worked in the pharmaceutical and nutraceutical industries before returning to school to pursue a doctorate degree. He graduated from Colorado School of Mines in 2014 with a doctorate in applied chemistry, with expertise in mass spectrometry, microbiology, and statistics. He then took a position at Osaka University as a research scientist for 3 years before joining JEOL USA 2 years ago. Sean has been working in the field of analytical chemistry for over 17 years. After receiving his degree in chemistry from the University of Illinois at Chicago, he started his career in large-scale synthesis using HPLC and GC techniques in reaction monitoring and purification. He joined Phenominex in 2003, working on-site for clients worldwide on method development, troubleshooting, and method transfer. He also started and managed Phenomenex's new applications laboratory. There, he drove innovation in chromatographic method development and many market segments. In this current role, Sean works on driving new solutions and support for the cannabis testing market and leads many efforts to improve analytical solutions for this dynamic market. Following the webinar, we will have a Q&A session and we will welcome any questions you may have. Please ask questions using the Q&A system to the side of your video player. If you experience any technical issues during the presentation, please contact us using the chat system. So with that, I would now like to hand over to Kirk and Sean.
All right, thank you for that nice introduction. My name is Kirk Jensen from JEOL USA, and I'm here today to talk to you about residual solvent analysis of cannabis matrix using GCMS headspace analysis. And I'm joined with Sean Orlowicz from Phenominex. Hello, Sean.
Happy 420, Kirk.
And happy 420 to you. So I'll be going more over the technique and some data, and Sean?
I'll be handling the chromatography side of things.
All right, great. So let's dip right into it. So basically, we have 3 goals here today with this webinar. The first is to give you an introduction on measuring residual solvents using GCMS headspace analysis. The second is we'd like to look at some standard data as well as some cannabis results doing the headspace analysis. And the third is we'll have some discussion on the challenges with this technique and maybe how to address those. And so to address those, here's kind of the schedule. I'll talk a little bit about cannabis testing and the solvents, regulations and limits, and then the headspace technique itself. We'll go into the methods. We'll talk about instrumentation, and Sean will talk a little bit about the materials. We'll also go into sample prep and the conditions we use to analyze. We'll go into the results, looking at the standard sample performance, and then I have some kind of interesting data to show you on a cannabis sample I measured. And then we'll get into a little bit about some tips and pitfalls that can occur when you're running this analysis, because it is a little finicky. And then we'll wrap this up. All right. So if you have joined any of the other cannabis talks that I've given, or have been attending this webinar series, you've probably already seen this slide. But for any newcomers, first of all, welcome. So we're talking about cannabis, of course. It's commonly used as a recreational drug due to THC as the psychoactive substance. It is still currently listed as a Schedule I drug by the US federal government. However, due to a recent surge in legalization, there's a huge need for analytical testing now, for regulation and testing. And so different jurisdictions that have legalized cannabis are starting to adopting different testing protocols for cannabis products. And so this webinar series was designed to help people who want to get into cannabis testing learn about these different kinds of requirements and testing protocols. This is kind of just an overview of what the cannabis testing landscape is right now. And basically, you could divide it into 2 different kinds of tests. The first is microbiological, so looking for mycotoxins and bacteria and stuff. And the second would be chemical. And within the chemical testing side of things, you have product quality. So this is going to be potency and terpenes. How good is the product for providing the high, and what kind of flavor profile it has. And then there's also a whole product safety side. And so here we're talking about pesticides and heavy metals, and of course, residual solvents, which is why we're here today. So let's talk a little bit about what residual solvents are. So basically, they're leftover chemicals that are used in some kind of extraction process. And so their use in the cannabis industry is, you're removing some kind of, chemical to concentrate it. So this could be terpenes if you want to get the terpenes out, or if you're doing CBD oil, you might be extracting that, or any other kind of extract that you're removing from the cannabis plant has to be done using some kind of solvent. And so, why test for them? Well, one is that you could be looking at the quality of your raw materials. So if you're testing residual solvents and you use, for example, butane to do your extraction, but you're starting to see some acetonitrile, that could be an indication that maybe you have some impurities in the butane that you're sourcing out. But of course, the bigger thing is the quality and safety of consumer products. And this basically comes down to what the danger of these actual solvents is. And so this comes straight from the United States Pharmacopoeia. There are 3 different classes of residual solvents. And so a class 1, these are definitely the bad boys. Want to avoid these at all costs. Known or suspected carcinogens, so cancer-causing materials, and environmental hazards. So obviously, if they're causing cancer to us, they're probably doing the same on a lot of wildlife. Class 2 solvents are to be limited. They might have some toxicity. It may be reversible, or it may be that they have a higher exposure limit. So they're not quite as dangerous, but they're still not ideal. And then class 3 are low toxicity potential kind of solvents. And so there's no health-based exposure limit, or the limit is so high, it would be almost impossible to be exposed to that much solvent. And so if we talk about, the regulatory limits, I'm going to use California as an example because they have a well published list. And the first thing I would like to point out before I get into into the chemicals themselves is that a category 1, even though it's lower limits and it's what California is focusing on, this does not coincide with the class 1 I mentioned on the previous slide. So only benzene and dichloroethane, which I have put an asterisk next to, those 2 are from the class 1 list from the previous slide. The rest of those are all class 2. And then in category 2, there are anything that has like a 5,000 ppm limit, like propane or ethanol. These are solvents that are actually class 3s. So that's why the limits are so much higher. But California has compiled this list of the 2 categories that they want to test for. And the category 1s, again, these are the bad boys. They're the ones that have the lowest, the harshest limits. It's 1 ppm. Category 2, there's kind of a range. Hexane is a little on the low side, but for the most part, these are very high limits and shouldn't be too hard to make. So we need a way to measure these solvents, and the way we're doing it is we're doing headspace analysis. And so at its very core, headspace analysis is essentially a chemical separation happening in a vial. So normally, if you're doing GC analysis, you extract into some solvent liquid and you just do a liquid injection. In this case, what's happening is that within the vial itself, you have the sample, and the volatile chemicals are basically turning into gas phase into the upper part of the vial, and that's what we refer to as the headspace. And so the efficacy of this is basically based on, volume, concentration, and volatility. So if you have more sample, you'll have more analyte in the headspace. If you have a higher concentration, you'll have more analyte in the headspace. And if your analyte is more volatile, it means it will it wants to go into the gas phase easier. And so it will, you'll get more of it in the headspace. And so essentially we're using this for volatile substances. And that's exactly what that list of residual solvents is that they're all, fairly volatile substances. And we're going to use the full evaporation technique in today's talk. And so basically what we're doing is that instead of adding like a liquid to the bottom or, some kind of solid sample, we're going to add a small amount of sample liquid to the vial. And then we're going to heat it. And this is essentially going to force almost the whole sample to be in the gas phase. And this is going to maximize the sensitivity, but also this is excellent for reducing matrix effects. I think many people know, but if you don't, cannabis done on a GCMS produces very complex data if you do the whole thing. And so, if you're doing pesticides, you want to look at just the pesticides. If you're doing terpenes, you just want to do the terpenes. And doing those things is difficult without getting a whole bunch of other chemicals. Well, headspace analysis is good for residual solvents because a lot of those matrix effects will not appear due to the volatility of the solvents compared to those other chemicals. And so now I want to talk just a little bit about the equipment that we're using. So we're using the JEOL JMS-Q1500GC, quadrupole GCMS. And our GCMS has large hyperbolic shaped stainless steel quadrupoles. So, and they have pre-filters. They're very robust. They don't break easily due to the stainless steel. We also feature high pumping capacity, and this is, great for getting the pressure down low. And also for, if you need to do any kind of maintenance, you can be up and running again very quickly. We got the fast scan speed at 22,000. We have a toolless ion source access and removal. So anytime you need to, change your GC column or you need to remove the ion source for cleaning, it does not require any tools to remove that. And it makes it very easy and quick to do. We have the usual modes of analysis. You can do scan or you can do selected ion monitoring or both simultaneously if you need. And we also offer a suite of software tools, for doing both qualitative and quantitative analysis. Library searching, all that stuff is available through our system. For the headspace analysis, we need some kind of injector, and we're going to use the HTA all-in-one GC sampler. And so this auto sampler does liquid, headspace, and solid phase microextraction all in one unit. In this case, uses a gas tight syringe injection for putting the sample into the GC. And it's, really fast to swap techniques on this thing. So 5 minutes, you could run a liquid injection, for terpenes, for example, and then you could swap it over and do headspace analysis fairly easily. Sean?
Yeah, thanks, Kirk. And if it's okay, I'd like to step in and talk a little bit about Phenomenex's expertise here. Here are some of the materials that we used in this project, and the devil is in the details for certain when we talk about residual solvent analysis. All of these small parts and pieces really matter, and they play a significant role in building robust methodologies. First and worth mentioning is that we used our standards from Absolute. Vials, we use 20 milliliter borosilica. You can get those from just about anywhere, including Phenomenex. When you preparing our standards and our calibrators, we use the Accuform tapered borosilica vials. And importantly, I believe Kirk and I have both fell in love with these mini inert valves that you can get from Kimball. They just make adding your standards to a vial a little easier. And as we deal with really volatile analytes like propane and butane, I find that these valves are very, very handy. When we do the analysis on the GC, I find that we do use a little bit of a specialized phase. In this case, we were using the Zebron ZB-624PLUS phase. Of note, we use a very specific format, and I'll talk about this a little bit later in tips and tricks, and that we use the 30-meter 0.25, 1.4 micron film thickness. And again, we'll get into that later. It's very important. The reason that we use the 624 in this particular case is, number one, the capillary silica is very deactivated, which gives us very good peak shape. It is very, very good in terms of bleed in a GCMS application. In addition, the 624 plus, as compared to a normal 624, has a higher temperature stability. Well, while that may not necessarily be important in the residual solvent case, should you be deciding to use the same GC and the same GC column for terpenes as well, you might find yourself going back and forth between a full evaporative technique headspace injection as well as a liquid injection. And in that case, baking out the column becomes incredibly important. Finally, we wrap that up with a good deactivated inlet liner. In this case, we use the Zebron Plus with a single taper with wool. Again, a liner is a small detail that we can't really overlook. But overall, these small parts and pieces really add to a good, robust method. Back to you, Kirk.
All right, thanks a lot, Sean. All right, let's talk a little bit about sample prep. So the idea behind residual or a headspace analysis, excuse me, is that the sample prep should be exceedingly easy. In some cases, you could just put, product directly into the vial, but in this case, we actually did the extraction on 1 gram of the flower into some DMA by sonication. Why would I pick to do this? Well, one, this is going to allow me to do the full evaporative technique, which I think is really going to help with the matrix effects. But two, it's going to also allow us to do it in the same way as the standard sample. And so we'd basically be adding so if we look at step 2, adding the 20 microliters, that's in both the standard and the sample. And so it's just the idea of keeping everything as similar as possible. And so it should be really easy to prep the sample. Oh, I can mention one additional thing. If you're doing the extraction into DMA, you may also be able to use that for pesticide analysis if you're also doing that. And so you may be able to just kind of take out a small 20 microliter sample for headspace and then send the rest off for pesticide analysis. On the standard sample prep side of things, like it kind of my slide here kind of belies all the work that really goes into this. Now, Sean just talked a little bit about the mini inert valves, and they are just absolutely critical for getting your standards to come out correctly. Because as you're making these standards, if you're not using this mini inert, you will, some of these solvents in the vials are going to evaporate. They want to go into headspace because they're volatile. So the mini inert really prevents that from happening and keeping your concentrations consistent. And so, but of course, doing that, prepping these standards takes a lot of time because, after you prep it, you have to put the vial on, and then you have to use that to make the next standard. And it's a very time-consuming process, but once done, these standards will carry you for a good length of time, especially if they're kept in a cool, clean place. And so it's essentially the same. Once you make the standard sample, you're going to add the 20 microliters to the headspace or to the vial. And you're doing all of this with gas tight syringes, which adds an additional, complexity to prepping the standard sample. And then you're going to measure the headspace using the full evaporative technique. Just a little bit on the analysis conditions. There's a lot of numbers here that, if you're doing method development, are going to be important. But just for today's webinar, I will just kind of highlight a few things. For the headspace sampler, we're using an oven at 60 degrees. That's going to help us put all of those analytes into headspace and into gas phase. And the syringe temp 150 to kind of keep them in the gas phase as it's transferring between the vial and to the GC. We used a 0.5 ml volume. For the GC itself, we're using a 10-to-1 split. That's something that can definitely be played with depending on what your method is, but it's a good starting point, and a flow rate of 1.5 mils per minute. For the mass spec side of things, we're doing EI plus at 70 EV. This is basically the standard mode. But when we actually measure the residual solvents, we're going to use selected ion monitoring for two reasons. Number one, that's going to give us better sensitivity because we can measure each ion longer. And number two, it's going to allow us to get rid of ions that we don't need. With residual solvents, you have a lot of low molecular weight ions. And so you can get a lot of interferences from, air passing through the column. Even if it's just a little bit, it creates a lot of noise. And by using SIM, you can basically exclude all of those air peaks and get good, clean data. All right, without further ado, I will move into the results themselves. And so this is just a 10 ppm standard sample. We're looking at a TICC chromatogram, which this is actually SIM mode. So this is TICC SIM. And I have labeled all of the compounds. Obviously, there's a couple where the names are a little difficult to see, and that's actually, almost on purpose, because those compounds are difficult to get to separate, even with a high quality column. You need to, your method development is really going to be key here. But this is also where we're really leveraging the power of SIM and the mass spec. And so if I show you just the SIM chromatograms for, those few that seem to overlap. Here we have methanol and ethylene oxide on the left. Those will tend to overlap, and we can see that they're fairly separated, and especially the methanol, we have no interference peaks. With the isopropanol and acetonitrile, we have almost complete separation, and once again, for the isopropanol, there's no interference ions at all. And when we look at benzene and 1,2-dichloroethane, again, we're getting almost complete separation along with very little in the way of interference ions. Let's look at a few of the calibration curves. I just picked the ones from the category ones, just just to show you guys what the cat ones look like. But we'll look at some numbers in a second that basically a lot of the other, all the other compounds also performed very well. So we're seeing strong linearity, all the way through our values. So we went up to 500 ppm, and we're still seeing great linearity even over a large dynamic range. And this is really the power of the quadrupole mass spec at work here. It really does well for this kind of analysis. Again, just to show you what the category 1 solvents look like, because they have the harshest limits at 1 ppm, I just want to show you that at a level below 1 ppm, we're still seeing all 6 of the category 1 solvents without any trouble, along with their qualifier ions. So we have the Q ion is the quantitative ion, and that's typically the most intense ion. And the I ion is a qualifier ion, and basically we're just using that to confirm that it is, benzene, for example, or it is chloroform. If you're running your analysis and you find that you're getting strong interference ions, you might consider looking at some different qualifier ions. You may be able to swap them out as the quantitative ion, because even if it's not the most sensitive ion, if it's more selective, if there's less interference ions, I think this will really improve your analysis. So I said I'd show you the numbers. Here they are. So on the top, we have all the cat ones. Basically, we have excellent linearity, 0.99 for our coefficient of determination. Area RSDs over 10 measurements are all less than 10%, which is excellent. And the IDL calculated for these substances is all actually less than half a ppm. So this technique should definitely be able to meet those regulatory limits, no problem. If we look down at the category 2 stuff, basically very similar performance. All the RSDs are less than 10%. The R squared values are 0.99 for almost everything except propane, and propane is a really tricky compound because it elutes so closely to your the air peak that goes through after the injection, and also it's just not quite as sensitive as some of the other ones, but definitely some good method development and good technique will help you push those values up even higher. If we look at the IDLs for everything, so almost everything is less than 1 ppm, and even though that's more than enough to meet the regulatory limits, definitely it's nice to see those IDLs so low. The exceptions, once again, propane, just because it's kind of difficult, and ethanol is also a little bit tricky. But again, the IDL is 7 ppm and the limit is 5,000. So there's no trouble meeting regulatory limits on that compound as well. So now, I know I've shown you the standard data. I want to show you this cannabis sample, and this cannabis sample actually has kind of an interesting history to it. So when I was measuring this sample, I actually was I was doing the pesticide. And if you attended my pesticide talk, the results came from this cannabis that we went and bought. Our headquarters are here in Peabody, Massachusetts, and in Massachusetts, that's marijuana has been legalized, and we can go to the dispensary, and that's what we did. We just went to a dispensary and got some stuff, and I set this up to do pesticide analysis, and did the extraction, measured it, and then I stuck it in our fridge and forgot about it. Well, that fridge is kind of used for a little bit of everything, and so it has all different kinds of solvents and stuff in it. And so I thought, as an interesting note to this project, I pulled that extraction back out just to see what it would look like, and it is absolutely contaminated, but from sitting in that fridge. And so we can see here on the TICC that there's obviously a few things. It looks like there's some methanol and some acetonitrile and whatnot. But let's look at a little closer. So here's the numbers. Definitely there's acetonitrile and dichloromethane and a little bit of some methanol and stuff too. The ones that I've highlighted in red, if I was testing this sample for California, it would have failed these two compounds. I just think it's kind of interesting because it's been sitting in that fridge and it just happened to absorb a lot of these different solvents in there. Even stuff like toluene and hexane, and acetone, especially acetone, we get tons of contamination from acetone because we're using it for everything. So even with the blank, we're still seeing acetone in this sample. And so I think the moral of the story for this slide is don't store your samples in a fridge for 6 months where you put just about anything else. So I'll just take a quick look at the 3 category 1 chemicals that came out. Actually, acetonitrile is not a category 1. You'll have to excuse me, but dichloromethane and trichloroethylene are both category 1 compounds, and they were detected. The dichloromethane failed, and the acetonitrile, even though it's not a Cat 1, also failed, and we can see the large amount of acetonitrile I found in the sample. And just to show you, so on the top, I have the matrix blank for all of these samples, and on the bottom, so we can definitely see that over time, that sample had become quite contaminated with these different solvents. Sean, I'll turn it back over to you.
Thanks, Kirk. And yeah, so as everyone saw, the method development done by Kirk was following some of the best practices in the world, and his data speaks for itself. So well done, Kirk. But Once we have the method development complete and we implement in the lab, well, that's when we start to really see some of the problems. And so I just want to speak for a few minutes on some of the challenges that we've seen implementing these methods into production laboratories, working with clients just like yourselves. So here's kind of the tips and tricks sections of this, and I think Kirk and I can maybe save everyone here a little bit of time and maybe a big headache. The number one challenge that we've seen in implementing this is contamination. And really, if I could put a finger on it, the majority of the clients that we worked with have found that the contamination for the residual solvent analysis has come from their laboratory itself. We all understand. Most laboratories are not exactly big places. We are doing residual solvent right next to where we're doing heavy metal analysis, right next to where we're doing potency analysis, right next to where we're doing pesticide analysis. Well, for example, if your HPLC UV system in which you're doing potency is nearby and you have a lot of acetonitrile sitting on the top of it, you might see a very common acetonitrile background peak in your laboratory. Conversely, something else I see a lot is that the exhaust from the electrospray ionization source of the mass spectrometer is not necessarily connected to an exhaust and is blowing evaporated solvent out into the laboratory. So really the way to I think the easiest way to mitigate some of the contamination that's from the laboratory is just be aware of where you're doing your solvent extractions. Be aware of where your HPLC solvents are. If you do have an HPLC, whether it be UV or the mass spectrometer nearby, I do highly recommend using some of these security caps. So you can put essentially an air filter cap on the mobile phase bottles themselves. But most importantly and commonly overlooked is you could put an exhaust valve on the waste container for your HPLC, which is probably contributing the most amount of solvent background in the laboratory. So this is just a mitigation device that I found to be very successful, especially when we're limited in terms of how far away our HPLCs can be. Second of which, do your extractions in fume hoods if you possibly can. Matter of fact, do everything you do with solvents in fume hoods if you possibly can. It's not only good for your residual solvent analysis, it's good for environmental health and safety as well. Other common techniques that we've used is bake out your glassware before you use it. Include an air blank and a matrix blank as part of your sequence and use that information to make some adjustments. And then also really commonly is take care with your gas tight syringes. I know myself, I've been guilty of just grabbing one out of the box and not necessarily checking it. And then maybe it's not operating properly and then my quantitation is off. And again, another common problem that we see in this analysis is really just separation related. While the JEOL GCMS is a very powerful tool, we still have to use chromatography to separate some of the more difficult compounds, as well as some of the isobars, which there are a lot of in residual solvent analysis. On the right here, I give a couple quick examples that are common. Benzene, dichloroethane. Maintaining really good chromatographic resolution between those compounds is important. As Kirk kind of showed earlier, methanol and ethylene oxide is incredibly important to separate chromatographically as they can essentially interfere with each other. And this is where really coming into play both balancing chromatographic separations as well as the single ion monitoring function that GCMS provides. Kirk mentioned this earlier, but I just want to reemphasize it. Using qualifier ions and qualifier ion ratios to your quantifier in order to add another dimension of selectivity so that when you do have matrix interferences, which these matrices can be very complex, that's another tool that you can really use to provide some selectivity for your quantitative analysis. The last part, in terms of chromatography, I want to hit one more time again. For this analysis, we purposely use a very thick film phase. And the reason for that are these very light gases, propane, butane, etc. By using a very thick film, we're able to get a little bit more retention. And as Kirk pointed out earlier, getting a little bit of retention of that protein to get it out of that air peak makes quantitation much, much easier. And it's a common mistake we see. And then finally, using the oven ramps and your flow rates to your advantage. In this case, Kirk did a great job, get great peak asymmetries and got really good peak shape in general, but you can utilize those variables in order to get better chromatography. And if you apply all these techniques and you build robustness, I promise you that you'll have much less headaches in the future. Thanks, Kirk.
All right. Thanks a lot, Sean. Really appreciate that. So I think we'll go ahead and wrap up and head into the Q&A. Basically, I hope that we've shown that, that you've learned what GCMS headspace analysis is, and that it's an effective method for measuring the residual solvents. Definitely the success of this technique depends on, careful sample and standard preparation, good instrumentation, high quality consumables, good lab practices, all things that Sean gave some excellent insight into. And I hope that you take those to heart because like he said, I think it will save you a lot of headache in the future. From the data, all the solvents from the California list were measured below the set regulatory limits, including the category ones whose limits are 1 ppm. And then we showed you an example of what a contaminated cannabis sample looks like, and that it can be measured with very little matrix interference, which is exactly why you're probably attending this webinar, is to see that. So I hope that this has been valuable for you, and I hope that you will ask a lot of questions. Before we head in, I'd just like to thank a couple of people from JEOL USA. I'd like to thank John Dane and Chip Cody for providing a lot of assistance with this technique. I'd like to thank SciEx for co-sponsoring these webinars. This has been my second pleasure to participate in this series, and it's been a blast, and the people have been awesome. I'd like to thank Phenomenex for providing the consumables we use, and for giving us the assistance and providing us help when we needed it for doing both the pesticide and the residual solvents analysis. And I'd like to thank Sean for being here today and helping and giving his input, because I think he's got lots of valuable experience to impart.